Good afternoon, everybody. So welcome to my presentation. I hope you enjoy the lunch. And today I'm going to talk about power and bandwidth efficient solution for next generation DVB system. This is my work during my summer internship at Thompson with my supervisor, Dr. Wen Gang. And this is a rating of the supervision of Wright and Larry. Okay, so here is the outline of presentation. So to begin with, I will give a brief introduction about the background and the motivation of DVB in general and DVB-C in particular. Then I will come up with two proposals that are quite different. So the first proposal is a revolutionary solution based on LDPC coded bit-to-bit modulation. And the second one is evolutionary one. It's a backward compatible solution based on hierarchical solution. I will spend much time on problem formulation part and present some simulation results, and finally we'll give a conclusion. Okay, so these pictures give an overview of the DVB project. So DVB stands for Digital Broadcasting. It was initiated by European Telecommunications Standards Institute in 1993 in France. And nowadays it has included over 270 members, including the system operators, broadcasters like BBC writers, chip manufacturers, and regulatory bodies. It has brought about one of the most fascinating developments in consumer electronics, and its aim is to reflect the best of both technical and business communities. And because of this, its application models evolves over time. So it starts with MPEG 1 and then go up to MPEG 2, and now it evolves toward MPEG 4. And the technology innovation in this project is largely driven by the interests of affiliated members, and it envisions its future mission as to build a content-based environment that can incorporate the broadcast services with the IP-based internet services. So this picture shows some of the features of DVB services. So as those long show, so this one is the DVB-S system, which means the DVB services is transmitted over satellite channels. This one is the DVB-C, which is transmitted over cable channels. And this one actually includes two different specifications. DVB-T is transmitted over terrestrial channels, and DVB-H is to convey those service packets over the mobile handheld devices. So the DVB services consist of a wide variety of programs which carried about different channels, and in order to have that powerful navigation capabilities throughout different networks, the packet structure is very special, and it's usually referred to as DVB data container. So you can see there are two parts here. SI is service information, TSI is program-specific information, and these two parts of information constitute the housekeeping information inside the data container, or in other words, they are the signaling part of this packet. The other part of this data container are the actual data. They can, they can be TV data, they can be video, audio, or data services, and all of them are multiplexed into MPEG transport stream and transmitted over different cams or channels. Okay, so that's the DVB container. So our focus in this project is for DVB-C, or in other words, next generation DVB cable systems, which is usually referred to as DVB-C2. 2 means second generation. So as its name suggests, there will be a first generation before this second generation. Then the question is, what's the motivation for us to develop the DVB-C2 techniques? And there are four folds of motivation for us. So the first motivation comes from the demand for higher spectral efficiency. So the first generation DVB-C only supported quad order, no greater than 256. It also supports 16, 32, 64, 128.
How did they, do they have OPM or
What?
how did they support that one order 64 now? Do they have OPM?
I think that's single carrier. That's single carrier transmission, not one carrier, because the first generation was activated in 1998 at that time, but yet it's not very mature technically. And but nowadays,
So Michelle, the previous slide is with this container.
yes,
Essentially, you're saying these are different versions of a source. Like it's like the same content expressed at different resolutions or something. Is that what?
not I mean, we are talking about this data, right? They are called multiplex because see when we watch TV, right? The video picture comes with the sound, but in source coding they consist of different data streams. But in order to do this digital broadcasting, they have to combine these two different data streams together into a package, which is referred to as data container. So data container is just a package, but this package, this structure is maintained through different communication channels, cable, satellite, or mobile sets.
Okay.
So does that mean that the same video stream is modified in some way to go over a satellite channel and a different way to go over a cable channel? That the modulation over the channel is the thing that changes from S to C to T? Or is the video signal itself
Yeah,
different?
the transmitter may be the same, but the different packets, they go through different channels. So that's what I'm broadcasting, right?
Yeah, maybe I can answer it. But I think in order to, because satellite they use different modulation compared to BBC. So if you want to deliver satellite program over cable, you have to do the demod and remodulation.
Oh,
So this is a high level structure for network layer, how they do the packaging, how they form the data packets. But on the 5-layer MAC layer, different systems, AC or TH, they adopt different configuration because of the channel. Right? Cable channel is much better than terrestrial channel, so they can afford very high order, 2056 in the first generation and higher in the second generation. Okay, so that's the demand for higher spectral efficiency. And nowadays there are some new services emerging, such as high definition TV, video on demand, and many personalized and interactive services. And all these services require higher data rates, and these higher data rates cannot be satisfied by the first generation cable networks. So because of this, the cable operators have a demand to either the desire for better transmission. And the second thing is that because we use a higher modulation, as the modulation order increases, the error rhythms or the vulnerability of the channel signal degrades. So because of that, we want to use more powerful codes to increase the power efficiency. So the first generation, they use shortened read-swallow code on size 2008 and 188, and together with a convolution of the field. But for the second generation, because we are talking about 1024 1K call and 4K call, so those mild channel coding is not sufficient. Therefore, we have to go to choose a more powerful codes, and LDPC codes, low density parity chain codes, becomes the attractive choice, and I will talk about that later. And the third motivation is from the perspective of system interoperability, because the same data container will be transmitted through different channels. Maybe we receive them from satellite, and then we do some relay and do some repackaging and transmit them over the terrestrial channel. And we need a system interoperability, which means the channel codes may be reused over different channels. And in that sense, if existing networks already adopted a very good channel codes, maybe we need to reuse them to satisfy the interoperability of the modulator, demodulator, channel coder, channel decoder requirements. And the last one is the backward compatibility with DVB series chip design and manufacture. And this is more from perspective of a commercial point of view perspective rather than a technical one. This is because this DVB project is driven by the common interests of all the members, so they have to consider the commercial perspective carefully. Okay, so this picture told us the evolution parts. The first generation is the C1, I call it C1. It was formed in 1998, but it will doomed to die sometime in this, maybe late 2009 this year or early next year. And okay, if it died, people need to come up with a different solution. So the first solution is, as I said before, is a backward compatible solution. So it doesn't destroy the original, the legacy receivers, but on top of that, they want to transmit more data. So they we can adopt a hierarchical modulation to satisfy the requirement for backward compatibility, and that's evolutionary rather than revolutionary twice. The second one will be more revolutionary, so that's the focus of this presentation. Basically, it can be called LD2C encoded bit modulation, and you can see the modulation order, the constellation order is really high. It can be 1K or 5K. Okay, so now let's come to the first part, the revolutionary part, the bit-into-bit LD2C coded modulation. So if we take the information theory from the WINLAB or communication theory from that, we know maybe 60, 70 years ago, Shannon has come up with this well-known coding theorem. So this coding theorem tells us that suppose this capital C, the bold C, is a code with rate R, and rate R, if it's greater than the channel capacity, the italic C, then the probability of error in decoding the code is bounded away from zero. In other words, so if we transmit the data at a rate which is greater than the channel capacity, then the reliable communication is not possible, it's impossible. And he also, on the other hand, he also proved achievability theorem for the coding theorem. And that tells us that for any information rate R, if it's less than the channel capacity C, and if there is a gap, delta is a positive number, then there will exist a code C or less n of data. So then I use subscript delta to emphasize that this then actually is a function of delta. And suppose this code has rate R, then the probability of error under the maximum likelihood decoding will be at most. The error probability will be outbounded by delta. So be careful here. I highlight the decoding maximum likelihood decoding because this is the optimal way to decode this coding. Question?
Oh, no.
But this theorem is very, very known, but there is the thing that it's not very constructive or it's non-constructive because it tells us, okay, there exists something there in the universe, but it doesn't give us the guidelines to how to construct and build such a code book to achieve or approximate the channel capacity. Okay, so after Shannon published this famous paper, researchers from both industry and academia, they have working hard to find good codes. So in order to find good codes, we have to go back to Shannon's proof and see what's the thing that's missing here. Okay, in Shannon proof, we know that he made assumption of random code. He assumes the block length of the code are large. It can be finite because the n of sigma, n of delta is unbounded. Right? And also it assumes maximum likelihood decoding, which is optimal decoding algorithm. However, in practice, if we combine these three ingredients together, actually it has a necessary but unfortunate consequence, which is complexity. In other words, in order to achieve or approximate the channel capacity using the coding strategy, Shannon has been adopted in proof. Actually, the complexity is prohibitive. So that means in engineering, that's not a good solution. But people, in order, rather than to bend our heads to achieve optimality, can come up with some optimal but good engineering solution. So the state-of-art good choices for the channel codes, they take the formats of long codes, structured, and pseudo-random. So that's the good choices for the channel code that can be applied in practice. And also, we require the good codes can be decoded by practical, but near optical decoding algorithm. Maximum likelihood decoding is optimal, but its complexity is high. It's easy to see its complexity actually is exponentially hard as the code block length goes to infinity. So the example of these good codes includes the turbo codes, which was proposed in 1993, and the LDPC code, which was invented by Zeller in 1960 in his PhD thesis, and revented in 1999 by McKay, etc. And these are good codes because these codes, they're long, they're structured, and they look pseudo-random. And in other words, they have good practical and some optimal decoding algorithms. The next picture shows us the decoding thresholds of the codes used so far against the channel capacity limit. So I think this picture comes from people working in NASA because you can read from the legendary Voyager, Galileo, Marine. There seems to be some projects they launched for the moon, for the Mars, or something else. But the good FTP codes actually come here. So it's very close to the Shannon ground. And in 2001, there is a paper published by Chang, and who have proposed IPC code, irregular IPC code, whose gap to Shannon limit is only 0.0045 dB. So that's very close to the Shannon limit, and that's good news for us. In order to describe the irregular LPC code ensemble, we need to use some terms or some descriptions dedicated to their degree distributions. So one way to look at LPC code ensemble is to approach the degree distribution from the age perspective. So the lambda x is the variable node perspective of this code ensemble, and the rho x is the chip node perspective of this code ensemble. And this is from the age perspective. This lambda I, the coefficients here, the nodes, fraction of age connected to variable nodes of degree I. So we use I minus 1 to denote the nodes of degree I, just subtracted by 1. So why we need to use this form? This is interesting because when we do the density evolution, and when we come to the irregular channel, actually this form can significantly simplify our analysis. So that's why people come to these notations. And on the other hand, we can also describe a code from their node perspective. So we maybe use LX, the variable node perspective, or the POX from the chip node perspective. And because these two sets of descriptions, they corresponds to the same LDPC code ensemble, there is 1-to-1 mapping rule between them. And these two setting formula just tell us how to go from one set of description to the other. So to give you an example, here is a hanging code. So this lambda p of x, this capital case actually tell us the degree distribution from the node perspective. So this hanging code, it has 7 random nodes. So if you add this coefficients together, 3 plus 3 and 1, you come to 7. That means the number of variable nodes on the left side. And this coefficient 3 actually enumerates all the sum of the trigonal numbers on the right side. And the exponents here actually tell us the degree of a particular node. So this is from the node perspective. And these two lower polynomials actually describe the same code, same kind of graph from the age perspective. But these coefficients are the percentage of the age. And this R lambda rho tell us this R is a rate. This rate can be uniquely derived from the degree distribution. So this case is for the hanging code with kind of graph is shown here. And this JK regulates the code. So at the same token, we have this very simple explanation. This is from the node perspective. This is from age perspective. And this is the rate derivation from the degree distribution over here. Okay, so that just gives us the general view of the code degree distribution. And in order to decode a particular IBPC code, we have to consider the suboptimal, and we have to consider a practical decoding algorithm. And in order to understand that, we have to take the first step towards the optimal decoding. So one of the optimal decoding strategy is the bitwise map decoding, which is in contrast to the blockwise map decoding. And for this bitmap decoding, actually, we transmit coded bit X over a matrix channel, and we receive a sequence, a vector Y. So this Y is a sequence, it's a vector, and this Xi is the intermediate bit. And after we receive Y, we need to guess which I on the ith position of the transmitted code bit will be the most proper one or twice. And we come up to finally boils down to this expression. And from this expression, actually, we have more practical decoding algorithm, because this one seems to be a one-shot decoding. It's like, okay, we get the vector Y and we guess X, but we have to enumerate all the combinations to do the factorization. So this is complicated. But from here, we can derive another decoding strategy, which is called message passing or bit propagation decoding. So this rationale for the message passing decoding is like something like this. So for codes which is cycle-free, which is also referred to as acyclic kind of graphs, the message passing decoding actually coincides, agrees with the bitwise map decoding. That's for the cycle-free case, which means there's no cycles, there's no loops on the bipartite kind of graph. However, when the kind of graph does have loops, this message passing decoding is no longer the optimal map decoding, but there is some, the airflow appears somewhere during the decoding process, because as long as the loop, the decoding process starts somewhere. But in general case, message passing decoding is good for us because we are happy after we conduct a given number of decoding iterations. And airflow openness, if the code is designed carefully, actually is not that bad. And we can use outer code concatenated with this code to treat the airflow, to improve the airflow openness. So the message, so this decoding algorithm is called message passing. So what is essentially the messages that is circulating along this code. So these messages are essentially some conditional bitwise distributed distributions, which can be denoted by these two element vectors. And the initial messages to activate this decoding algorithm actually come from the channel So if you look at the previous pictures, you see, so this part, this is the variable codes, and these are coded bits connected directly to the channel. So in the first decoding iteration, the channel input activate this AND side, and then these messages are transmitted along this edge toward the chip node, and then it transmits back, and then go on go forth. And finally, hopefully, will converge to some good guess about the transmitted coded sequence. Okay, so this tell us what's the basic object rules. So in the previous picture, we showed that the essential messages can be a vector. These vectors are the conditional bitwise probability, but we can simplify that because by taking the ratios of these two elements, we come to the log-negative ratio. So this one is beta obviously. Why? First reason, these two actually they are vector, the two elements, but the LU is just a ratio, is a scalar. So we love scalar more than vector because it's simple. The other thing that numerically this one is more stable because if this one is very large, this one is very small. The quotient is very large, right? If we transmit these two of them, actually the numerical stability is not good, and the conservation effects will be very pronounced. However, if we take the bulk of them, we can actually compress the dynamic range. So usually, when we talk about message passive decoding, the messages exactly used in this decoding algorithm is the log-back relation for this one. So take the ratio of these two messages and take the log. And this one is the messages that's most frequently used in this decoding algorithm. And we can see this LU actually they can be one-to-one mapped to the two set of original messages, which means if we know the log-back ratio, we can divide the two conditional probabilities conditioned on 1 and -2. And these two pictures at the bottom show us the updated goal for the log-back ratio. So this arrow, black arrow, is output edge, and this one is for the channel. So this node usually use a circle to denote the variable node, except the LR channel combined with this one. This one comes from the chip node, and then they calculate the output. So because we use LR, actually the output is just the sum of these LRs. And this is for the variable node side. And on the chip node side, we already use a square to get the chip node side. It's more involved, but it can also be simplified a good deal because it's just a percentage function over here. So this is like a product. And this is sum, that is product. And that's why message passive decoding is often referred to as sum product algorithm, because sum and product are simply the two object rules that's used on the variable node side and chip node side. Okay, so we know whether a channel good, especially for analytic code, is good or not. It depends a lot on how we design them, right? So because we already use the finiteness codes, the degree distribution is more important because if the code is very long, it's infinite long. We do not care about degree distribution that much because we know random code is always good. But in practice, in applications, we always use the finiteness codes. So the good structure is very important for us. So what are the common features for a university good advocacy code? So usually irregular advocacy code outperforms regular advocacy code because they are more akin to the random code. So usually the universal good advocacy code, it will have irregular variable node distribution. And second point is that the code length should be not too short, which means the code block length has to be moderate or long. And also, because we use this suboptimal sub-product or message passive decoding algorithm to decode these code words, And we know the sum product action is suboptimal because if you start at some training sets, then a good accuracy code must exceed good error performance or error flow performance on the message passing decoding. So a pronounced example of good LDPC code is DVB-S2 LDPC code family. So S2 means signal generation satellite. So why this LDPC code family is good? Because it offers us two different kinds of long lengths. The first length is 16K, the second type length is 64K. So they're sufficient for most applications. And also they cover a wide range of rates. The lowest rate is 1/4, the highest is 9 to 10. So that's wide coverage for different applications. If the channel is very poor, we may resort to the lower rate. If the channel is good, it will go to the higher rate. And also this code belongs to the family of structured, irregular repeat cumulative code. So this SRIA code actually is very interesting because it's a hybrid of LDPC code and turbo codes, and it inherits the virtues, the good features of those two classes of codes. And this code, as its name suggests, is developed for satellite channels, but it has been adopted to be reused over terrestrial and cable channels, most from the perspective of codec interoperability. Okay, in order to study the given code ensemble under the message passing decoding, we need a mathematical tool, we need an analytical tool, and density evolution is one of them. So basically, density evolution is a statistical technique to analyze, to study the performance of a code ensemble on the message passing decoding algorithm. So in order to do that, we have to know what's the degree distribution of LDPC code, which means we have to be given a code ensemble description. And we also need to know which channel this code ensemble is transmitted over. And the requirements for this stable channel is it has to be static, it has to be memoryless, and it has to be symmetric. And what's the density evolution basically do? It, as its name suggests, it's density evolution, so it computes the evolution of the density. And the density is about the PDF of the messages, or in other words, the PDF of the likelihood ratio of the decoding process. And density evolution can determine for given channel quality whether or not the decoding bit error probability approaches zero as the block length and the number of iterations goes to infinity. So from this possibility, you can see that actually this tool really helped us a lot because the code ensemble, the traces for the code that satisfy the code ensemble degree distribution can be infinite. So how can we know whether this code, this large code family is good or not? But if we use density evolution, right, we do not need to look at a particular kind of work. We look at a family, we look at a larger group, and we know on average how this group behaves. And if it's good, okay, we take it. Otherwise, we forget about it, and we redo the design process. So that's why we need to resort to this density evolution. We said that the DVB-C code will be adopted for reuse over terrestrial channels, but the cable channels. But this code is designed for the satellite channels, and the question is that good enough for cable channels? And if not, what are the technical challenges for resuming DVB-C codes over cable channels? So the first thing is that the spectrum efficiency is different. So for the satellite channel, right, when the DVB-C codes were first developed, the highest information order it supports is 32 ADSK, which means 5 bits per channel symbol, right? However, when it comes to the DVB-C2, we require 4K quad, which is 12 bits per channel symbol. So that's a big gap, that's a big difference. And we really need to come up with some strategy to reduce that gap. The other thing that we know the cable channel is pretty benign, right? The cable channel is no such very serious selective channel fading, selective time fading, time selective fading, but still there is a power constraint on cable channels. So nowadays, most of the cable channels deployed, they have an upper bound for this SNAR, which is no greater than 40 dB. And as I said at first, at the beginning of this slide, the DVB-C codes is not optimized for higher order modulation. And because that is a mismatch, it leads to a higher decoding threshold, which means, okay, for the 32A PSK for S2 application, we can decode it very efficiently. But when we directly use it to the cable channel, maybe we have to pay for higher power, right? So that comes down to the power efficiency, and that's not be hopeful. And the other thing that, because of the higher constellation mapper, actually, we look at different bit level, different layers, actually the error protection varies a lot. So if we directly connect the code to that higher order constellation mapper, so we'll come up to a very high error flow. And this error,
Michelle, this kind of a picture here, maybe you're going to show that it's kind of missing. Okay.
is this happy?
Yeah, so okay. So
Right. So previously, the point I'm trying to make is that we do not plug these two navy blocks here. So what are the problems we have? If these two blocks are missing, so these two blocks are our contribution. These two blocks are the way we will be used to, to shorten this gap.
but somehow you're going to design this interleaver,
Yes.
these blocks, in response to different versions of the QAM modulator.
Yes.
Like if it's one QAM modulator, you'll have some systematic procedure for designing
Yeah.
interleaver.
Yeah. The design methodology is generic, but when we fix the order of cosmetic, we have to change this.
Okay, but what's the motivation for saying, oh, the BCH encoder, the LDPC encoder, we don't want to touch those? But what's the?
Actually, I took that before.
You
That's
said that
because we need
before,
to.
but
Yeah, we
now that I
use
see the picture, I have to.
Yeah, I will reference because these codes, right, the DVB-S2, these two set of codes have been specified, have been adopted in the S2 standards, and the chip manufacturers make chips according to that codes, right? And nowadays, people come to the cable network, and they want to reuse those chips. And the other thing that these codes are really good. Although they developed maybe 3 or 4 years ago, but they do exhibit a lot of virtues. They are structured, they have sufficient block length, and they have wide coverage code rates. So I guess
So they were designed for just
Software.
for like a BSC type channel, like a binary symmetric channel.
I think this also found that AWGN channel.
So they're
Software.
designed for, well, that's the same thing.
Yeah.
So they're designed for AWGN channel,
Yeah.
right,
For the
without
satellite
any,
channel. Yeah.
no time variation, no.
Yeah, but it turns out that it also behaves very well on the terrestrial channel if we design this thing good. So we know from the channel perspective, the capacity shading strategy is to cluster them all. I call them signaling, Gaussian signaling, right? So Gaussian signaling doesn't distinguish between the channel code and the modulator. So that's the capacity shading thing. But that's the theoretical part. In practice, usually people will, decouple their design. They choose a particular code and they tweak the modulator, and then they tweak the modulator and they change the code. So that's maybe not the optimal way to achieve capacity, but it's a good way to do engineering, system automation. And we won't believe it, but this code, although they developed for the AWG back channel, but they really do very well on terrestrial channel. If this one is is designed carefully.
All right.
Maybe just item. You mentioned it's designed for satellite, but also adopted in the DVB-T2. So that's in the terrestrial TV broadcast environment. So that's actually the major reason is they also want to use the same code because they want to build a chip has the dual demodulator. So that can decode the DVB-C.
What?
This is President. Can you guys say this slightly closer to this microphone?
Yeah, sure. It's funny, we had no trouble recognizing you, Frederick. We
I don't know how to.
just put it, maybe, I was sitting way in the back of the room, but I can move up front.
Sure.
You hear Michelle okay, right?
Michelle, yes.
Okay.
How about, did you hear Wen okay? Wen was,
Yeah. Let me get this. Do you have anything to say?
nah, we're all done. We said our important stuff while you
Larry,
couldn't
do you have
hear.
anything to say? No. Okay. Now it's my turn. Okay.
Hey, could you hear Larry just now?
No.
Larry's
Hi,
short.
Frederick.
Hi, Larry.
Okay.
It's not clear that turning it makes any difference.
I don't know what you did, but I can barely hear anyone.
Because no one is talking now.
Could you hear that?
Most important that I hear Michelle, so.
Never mind. If you come back next time, I'll do the Pokemon again for you. Okay. Okay. Now let me continue. Okay. So that's the trick behind our scheme. That's the impact. But so because I put a big interleaver here, so you can refresh our mind. What did we learn from all the communication course? What is about interleaving? So this slide tells us something about the effects of bit interleaving. So bit interleaving essentially is a simple procedure for arranging the order of bit sequence, right? So in contrast to the simple interleaving. Simple interleaving is like, okay, we permute the order of the symbols, but bit interleaving, the elements of operation is the bit, coded bit, the binary bit. And bit interleaving is widely used in wireless and wired communication for various purposes. For example, it can help us to decorrelate the channel feeding, the burst feeding by randomizing the profile. And the typical application is a bit interleaved code manipulation. So it was initialized by the Harvey, right, in 1993, but it's later, Carrie, Giuseppe, is his name that pronounced like that?
Giuseppe
Giuseppe Carrie. He and his colleagues did more in-depth analysis about BSCM, and now BSCM is widely used in industry, a lot of applications. And the second role of bit interleaving in this communication system is that it can help us to enlarge the minimum distance of concatenated codes. And the typical example is the turbo codes. Turbo codes, there are two constitutive codes. They can be parallel or serial connected, but in between them, there is a interleaver. And the end of that interleaver, the goal of the interleaver, is to help us to enlarge the minimum distance of concatenated codes. So we know the code, whether the code is good or not. A lot of things depends on its distance, or in other words, its distance spectra. So if we given the code rate and the code block length, the one that can provide a larger minimum distance is the one we love. Okay. And the third role, that's the focus of this topic, that the bit interleaving can help us to match the irregularity of a channel code profile to the non-uniform channel. So we, in general, we call this bit interleaving, but essentially we do some bit demultiplexing. So what's the difference between bit demultiplexing and bit interleaving? So bit interleaving, generic, it means random, right? We do not care about the complexity to do this computation. But when we talk about bit demultiplexing, we impose some structure over there. So that's the difference. Okay, so when we talk about the high order quad, and when we want to do this decoding, so it's very important to know what's the high order quad actually can help us, or what's the difficulty that can make obstruct us. So if we take the 1K quad, for example, so 1K quad, it consists of 10 bits per channel symbol, and if we consider the symmetry of the I branch, invert branch, and the quadrature branch, actually there are only 5 distinct bit labels. So these 5 curves just illustrates the different bit label capacity of a particular layer, right? So the 5 bit, if we look at the bitwise neutral information, so how much is that? So if we look at the constellation in the Euclidean distance, right, the average Euclidean distance is different. And that translates to different bitwise reliability if you look at the LLR. So this curve is about the LLR, the bitwise reliability for this high order constellation vector. And the second plot on the right shows us the bitwise capacity. So you can see, although this unit may be different, but the order is the same. So the top white blue curve, and this blue curve is the MSB, the most significant bit. The bit, if we look at the bit which has the largest bit distance, and the bit that is protected receive the best protection from this channel mapping, right? Okay, so we can see, okay, these 5 bits are different. And these 5 bits represent 5 distinct bit labels, and they sort of give us a parallel, non-uniform channels. So parallel channels, the thing we're happy about that, we can do water feeding, right? If we give them power constraint, and we give them a state of parallel, non-uniform channels, we know how to achieve capacity, right? We do the water feeding. Here, we use a notion similar, different from water feeding. It's like, okay, now our resource is the irregular error protection of a code, and how we distribute those irregularity of the code profile to this non-uniform channel. How we assign a particular code bit to a particular channel label, right? And then to harmonize or to uniform this error protection and make this coded population as a whole achieve good power and spectral efficiency.
So this 5 channels, you mean there are only 5 bits?
Right. I think I gave this picture before in project class. So this is the 1K quad, right? So 1K quad means 10 bits will be mapped to an individual symbol. But now we consider the square quad, which means we have the index and the quadrature. And each branch will have 5 bits. Because they're symmetric, and you know that actually the index and quadrature, they are the same if we label position the same. So this 10 bits boils down to 5 distinct bit labels.
What is BRGC? Gray code.
Oh, BSCM, oh sorry, this is the shorthand for the binary reflected gray coding. There are some very interesting papers about this labeling stream, because usually we assume the gray labeling, right, is the best thing to do, but it turns out that even for gray labeling, there are different kinds of gray labeling, and their performance is different, especially when the concentration method goes higher. If we only do the 60 column, okay, the gray labeling may be unique, but if we increase the concentration method as we go to 1K column, 4K column, okay, different reliability strategy comes up, and each of them will have different performance. And some people have proven that this BRGC, this binary reflective gray coding, if we use this as a reliability strategy, it will achieve the best performance in a one-shot population if we do not do the iterative receiver between the demodulator and the decoder. So that will be the optimal choice for this receiver structure adopted. Any question?
Your parallel channel thing it's a nice analogy, but it's there's quite a few differences, right? because you have dependency in your errors, right?
Um,
Whereas in a true parallel channel model, right?
Yeah, yeah.
You have independent
Yeah.
errors on the
I
channel.
think it's more akin to the paper you write, the deterministic, the correlated.
Yeah, well, that's what I'm wondering. And then the other one is, you know, in parallel channels, you talk about water filling, right? But the result of water filling is that you get different amounts of mutual information through the channels. This is really more analogous to the capacity of each of those channels after you do the power allocation. Like because you don't have any flexibility here to put more power or more of some resource into one of the channels. The fact is the channel is now at a particular level is really at this point given to you by it conveys this amount of mutual information per symbol, you know, for a given SNR. But let's keep moving because I have to really leave by 2:30, and I don't want you to.
Sure. I think
I
okay,
don't,
so
you know.
go a bit living. If we look at in detail, do something like this. So this is an irregular code on the left side, right? On the right side, there is a call later. Here we change to the 256 because it's easier to visualize. So for 256, there are 4 different big labels. So as SNR goes up, you can see the 4 big labels. And if SNR is very small, actually, maybe the LSD, right, in weak label, the capacity is 0. So actually, they're not useful at OSR.
Michelle,
Yes?
somehow the sound went down just a minute ago.
She went closer to the screen to point at something.
Yeah. I think you know this picture before. You look at it, you feel familiar. I will try to close to the. Okay, so the simple explanation for idea based on the previous picture. We can now change the connection between the variable node and the check node. Why? Because that internal commutation is specified by the pantograph, specified by the code. Because the code is given, the variable node and check node, their connection is given, so we cannot change that. But the thing that we can control, we can change, is the connection between the variable node and the constellation library. So look at this picture. So the orange arrow is the error come from the channel, right? But these things are from the code itself. So for this part, these are the inner connection between the variable node and check node that we cannot change. But this one, the edge to which we connect the coded bit to the channel level, that's something we can control. That's something we can do maybe smart things, right? Okay, so there are 2 important points. We know the random bit interleaving is good, right? And we are familiar with in the channel feeding, the bit interleaved coded modulation. For the BSCM strategy, they assume the bit interleaver is infinite and they are random, purely random. Random bit interleaving is good, right? Because it's like randomize the cyclic profile and make the code performs like the random code in Shannon proof. But in practice, random interleaving is not good because it involves a lot of complexity. We have to remember the positions, the commutation positions for each coded bit position, and then do that at the receiver side and at the transmitter side. So that's theoretical, desirable, but practically impractical. So we desire some structured bit interleaving, and that's why now we change the notations from bit interleaving to bit demultiplexing. Okay. Then the question is how to design a structured bit interleaver. Structured bit interleaver means demultiplexer for the 4K quad, right? So what's the basic approach we should use to solve this challenging, this hard problem? There are 3-step procedures. The first step is to start with a suitable code ensemble. This ensemble must be good, right? And then after that, we'll choose appropriate channel model for later, for easier analysis. And then we'll apply a trackable analytical tool to analyze, to evaluate whether this design, bit interleaver or bit interplay demultiplexer is good or not. Okay. So the first step, we'll start with the structured IRA code. So this code, as I said before, is a hybrid between the LDPC code and turbo code, and it inherits the vertices of these two different classes of codes. And the other thing that it's very structured. So this picture shows the paradigmatic matrix of this SR code after some row and column implementation. So although you still think it's random, but I will feel very happy because for me, it looks very structured. See, this part, right? This part is the variable node, information bit. That's the systematic bit for the paradigmatic matrix. And this part corresponds to the parity coding bit. So it says that because from the paradigmatic matrix, we really know the degree distribution of this kind of graph. We can see that all the degree 2 nodes corresponds to parity bit, and all the high degree nodes corresponds to the information bit. And also, if we zoom this picture a little bit, you'll see actually each one will be some superposition of the offset of the diagonal matrix or identity matrix offset something and superimpose them a little bit. And this structure is very helpful for us. And because of this, actually we can employ a very useful framework which is called multi-edge type setting to do the demultiplexer design.
So these pictures, right? I mean, I'll reveal what an idiot I am. What are they? Like they actually represent, does each little speck represent a place where
I think
a variable node is attached to a check node?
Okay, so this is a paradigmatic matrix. So paradigmatic matrix, if we look at it in algebraic way, right? It's a matrix, there somewhere, one somewhere. And because it's a low density, so we expect that we only see a small bunch of zeros and a large bunch of
Small
zeros.
number of ones.
Yeah, a small bunch, sorry. And this picture just shows that, okay, if we look at the paradigmatic matrix, so this row corresponds to the index of variable node. And this one corresponds to the index of check node.
So the little colored specks going across a row are the places where you have ones with respect to.
Yes, if there's a blue box up here, that means, okay, there is an edge from this variable node to the check node. So the intersection of these two qualities.
So a random thing would just look like a random speckly pattern, like raindrops.
Yeah.
Okay. And so what do these diagonal lines mean? What do they?
This
like
diagonal is just because this is very long thing. So if I zoom here, so it's like that. But this means okay. It means okay. This check node, this bit. Row-wise, this means, okay, the position of the coded bit in sequence, right? So this means, okay, for example, if you take this floating solid bit, for example, this bit will be a parity bit. And this parity bit, it will go through two check equations. Because if we draw a line here, it will intersect twice with this blue diagonal. Right? So it's like, okay, so how we view the connection here, if we want to see for a particular variable node, for a particular code division, so how many check nodes it goes through, and to which check nodes it will connect to, we just draw a line here, and we see the intersection.
So let me ask this question. If you have in some place just one, is that upper right-hand corner, like, is it really white and empty? Or is it that there are individual little specks that represent? It isn't. So it's not like, an individual speck by itself would be actually invisible on your resolution.
After the regionalization, this is called structure. Okay, this part, if we zoom them, they're just some small blockwise, the diagonal. This part is empty. The only non-zero entity is just along diagonal. So they are very structured. And because of this structure, we can imply this NET setting. And then we do the demultiplexer. So what's the demultiplexer? if you look at this picture, it shows us something, an idea about that. So this length, this from here to there, that's the length is the block length of the code, right? So from here to there, it's like, okay, now we have a given code, the coded bit, the position, variant some way. What's the demultiplexer must do? The demultiplexer just partition them into uniform text blocks, and then map a particular block for given color to a particular bit label. So rather than randomly leaving, which means okay, we randomly bit arrangements in arbitrary way. Now we do a systematical systematic rearrangements of these codes. Just chop them into uniform length pieces, and we distribute the whole yellow one to a particular label, and then the green one. But they do not need to be continuous in the order. There can be some connotation of the bit labels that these chops are assigned to the concentration. So that's what our demultiplexer will look like.
So this modulation order would be 2 to the 2Q or 2 to the Q?
2 to the Q.
Okay.
Question?
So the number of bits you assign to level 1 is the same as the number of bits you assign to
Yeah.
level 2
Yeah.
and so
Yeah,
on?
why? Because we now
Because every symbol carries
the,
a level 1
exactly.
bit, a level 2 bit, and so
Yeah.
on.
For a 1K column has 10 bit labels. So each bit label must correspond to the same number of coding bits. We do the coding first, and then we assign these coding bits to the concentration mapper. Right? So suppose we have, for example, if we have a coded sequence, it's 100 bits, and then we have a concentration mapper whose order is 1K. Then we will have 10 1K sequence, right? So that means each different bit label will receive the same amount, same number of coded bits.
So ultimately, do you end up having a model where each code word, each LVPC code word has about an equal number of bits from each level?
I
That's
think
good,
I
right?
like to inverse the order you were talking about. It's like, okay, now I regroup code bits into equivalence subgroups and assign each subgroup to a particular bit label, a layer, so as EU deterministic model. So it's like, okay, now the label, the layers of a symbol is fixed, and the code bits, the number is fixed. Now I just randomize the starting positions. This what's called lambda? No, it's not lambda. Whatsoever. I just choose optimize this one. Right? This one, it's like the starting point. It may be a random thing.
Yeah, sure.
This is a random thing, and the order is like, okay, whether this orange comes to the NSB or LSB, that's our choice. And that thing is also an optimization parameter.
So I'm kind of confused by. I remember reading this part. So you have this big block of bits, right? And you
so
choose
the
a random.
codex is the codex. If that's the 16K bits, that means from here to here. If you look at bit one, the length is 16K. But these Q groups means now we have Q layers, unlike EU deterministic channel model. There are Q different layers,
I
and
understand
each
that.
layer receives the same number of bits.
Yeah. Okay. So I understand that. So the question is, how do you collect those bits? So you collect one blue bit, one yellow bit, one green bit, one
Yeah.
purple bit,
Yeah.
and then you transmit a QAM symbol.
Yeah, it's like, okay, take the first one from this yellow group, take the first one from the green group, take the first one from the purple one, and then form them together into the same channel symbol, same clock symbol. So the degrees of freedom we have is the initial point here, this parameter. and the order of this, the mapping order of these blocks in block sense. That's a twofold of degrees of freedom we have for this demultiplexer design. That's the parameters that we can difference.
Okay, I think I understand now. So let's
Okay. I think I'll try to rush. And for this demultiplexer structure, if we extend, because this part is the generic package kind of graph, but this layer is something of a contribution. We added another layer, the channel. See, this channel 1 to channel Q corresponds to the Q different constellation map labels. So it's like now this part, the connection, the edge connection between the variable node check node, this part is specified by the pantograph of the code. This part we cannot change, right? But this part we can change. And our multiplexer will help us to do the optimization for the connection between the coded bits to the published method, which boils down how do you do the implementation from this layer, variable layer, to the channel layer. So the function of the demultiplexer is focused on this part.
So Michelle, I can make an example. I'm sorry, but are you doing the MDPC with the pure symbols or
Q quiet symbol, yes.
Yeah, so it's not binary.
No, it's not binary. It's
So everything is on the
higher modulation, yes.
wait. So just hold on a second. You're saying that you have a Tanner graph that describes
Yeah, this one.
the decoding of. Well, okay, you pointed at the beige colored object labeled 1-1 and called that a Tanner graph. Is that correct? The whole thing
Maybe
is
not strict one, but the best. So what the Tanner graph actually corresponds to this one. But because of the structure, actually, we do not need that many number of H class. For this SR, there are only 2 different H class, and I colored it at 2 different colors.
In this one, there are only 2 different edge classes
Yes.
because.
Yeah, if you look at this picture, it's difficult to say. So how many edges, capital A you have, right? So the edge is like line, and they maybe connect to different sockets. So this H1, this circle is vertical socket, and this square one is a chicknode socket. So this is like, okay, now we connect a wire to different 2 outlets. And
You're talking about this is a structure derived from
this one.
the LDPC code,
Yeah.
and that has nothing to do with the interleaver and nothing to do with the clamp.
This is an inner structure of the
Okay.
stone. But usually it's not that simple. Here we only have 2 different colors because we only have 2 different classes H, and that's thanks to this code. But for generic LDPC code, maybe we need solid colors to distinguish those different H class. So
Okay.
this multi-H has this.
So here on the right, you're using colors to distinguish types of edge classes in the Tanner graph,
Yes.
right?
And this
But over
is,
here, you're using colors to distinguish assignments of bits to different clam levels.
Mhm.
But am I wrong that the 2, there's no relationship between
Yeah.
the fact that you
This
use
color.
the brown and the brown and the green and the green? That's just, you
Yeah.
kind of coincidentally confuse the heck out of it.
Actually use a different color. Say, okay, so this color
Okay.
should correspond to, so
Alright.
at some sort of these,
All right, let's, I think, okay,
Sorry about that.
yeah.
Okay,
At
and
least
now,
I figured out why I was confused.
hope you're doing better. Okay. Now we need to tend, say in the previous picture, say our 3-step procedure. We start with code ensemble, we choose the SRR code, the multi-edge capacity. And then we need to choose appropriate channel model and apply a magnetic control. And this picture essentially tells us how to do the last two tasks. So basically, we use density evolution. So as we said before, density evolution is used to study the evolution of the PDF of the LR messages under this message parsing decoding paradigm, right? So density evolution is maybe our unique tool, I think, for most coding people to study to do the performance analysis. But in order to do the density evolution, we need to make some assumptions about the channel. We have to assume those channels satisfy the symmetric condition. And because it's channel symmetric, we can as a result, we have the concentration theorem. So concentration theorem is that in order to study the performance of each code word over this concentration method, we can only observe the performance of O0 code word or O1 code word. Use it as a representative of the average performance of the entire code word. Right? So that's the simple thing. That's the beautiful part of this density evolution and the concentration theorem. But in order to do that, we have to symmetrize or make our channel symmetry. So this symmetry is different from the BSC symmetry. It's different from the BEC symmetry. It has a specific definition in terms of the density of the LR. So I forgot to put equation here, but if you're really clear about that, maybe I can show you in some other reference. So that's channel symmetry for this density evolution. It has specific definition. And for binary modulation, it satisfies that condition automatically. But now we're talking about multi-level modulation. So that's different. So why? I think intuitive explanation. So suppose now we have a O0 code word, right? If that O0 code word represents the representative of the whole code book, no, why? Because this O0 code word, if we map them to a constraint macro, they only come to a particular configuration point, right? But if we choose the other code words, they'll be mapped to the other, maybe the far corner or maybe the central part. So these code words will exhibit quite different performance. So this O0 code word, if we do not use this here, actually, it's not representative. So by studying this O0 code word, we cannot predict the performance of the whole code book after this classic code. So in order to overcome this problem, we'll use this channel adapter. And once we plug the channel adapter here, we can prove the channel symmetry condition is satisfied. So for the calculating,
how many slides do you actually have left? Maybe I should try to rearrange my life. And
how many minutes do we have?
well, so the question
10?
is, yeah, so I have 10 for sure, but
Okay, I will rush.
how many slides do you actually have? Tell me how honestly.
50.
You have 50.
I will rush. So
Well, so maybe I should try to
okay. I think I have covered the essential part, like the most important part. So the other part is the tricky part. So I will rush. Okay, so this is about the surrogate channel notion, right? So we know the BSC is
let me step out like a phone call.
okay.
And see if I can.
Do we need to wait for you?
Yeah, hold on.
So you are assuming that each symbol experience is an independent Gaussian channel. Each
Yes, by BI Decoding.
that's for the cable. Is that
Yeah. It's too many.
50.
I tried to skip some of them, but it seems I can't. Sorry, I have full control over my presentation.
Why not?
I think I have full control over my, rhythm, pace of my presentation. So,
Roy's fault, he asked me a question.
I hope you don't ask me questions at this moment because I think a lot of people here are in a rush to leave.
I think you gave this presentation earlier.
Yeah, so I think Sylvia is know what's happening, well, knows what's happening here, but maybe Roy maybe not. very difficult because maybe I should send them the slides last night. That would be do better. But only finished slides this morning is recalled, so it's too late. Sorry about that.
Okay, thank you. I made so we can. I'm
How long?
I have no, so I can now stay. I thank my children.
Okay.
But
I
I'm a little bit sort of like, I mean, we usually make these things try to be for a master's paper an hour. But on the other hand, and we're at an hour and 20, but
You're at fault, right?
I don't think so. I think Michelle sort of spent too much time on a lot of background. But maybe I'm kind of interested in having this tutorial. So, but I on the other hand, I think there's something not quite correct about having it drag on, go on and on and on in terms of what the event is supposed to be. So I'm of mixed feelings to say, okay, now you don't have to rush.
Well, why doesn't Michelle give you a tutorial in private?
Okay, so you prefer it would be better if she moved more quickly. Yeah. Okay, so let's move quickly. So we should be finished. Let's not try to go all the way to 3. Let's be finished well before Larry's.
Sure, I'm going to try. Okay, so this
Thank you,
is
Larry.
Thank you, Roy.
this is the surrogate notion. So why we need to use a surrogate? We know BSC appears to be simple, but it's not simple enough because when we do the density inclusion, actually, we have to track the density, which means the PDF. We know the PDF is defined over continuous space, so it's difficult to track that infinite algebra problem. And rather than do that, we desire to track some, trajectory over a single scalar, and that can help us a lot. That can simplify our life a lot, and that's why we need to invoke this surrogate BSC notion. And then the question is, how will you substitute BIAWG channel actually here to equip BSC? There are several ways to do it, but our way to do it is to make the capacity of these 2 different types of channel equal. That means, okay, if I know this channel capacity is something between V and C here, I derive the error probability of the surrogate channel using this formula. And then we come to equivalent in some sense, the surrogate channel, and then we will move the density inclusion from this channel to this channel. And that will simplify our life a lot because, as Project told us, as Silver told us, the density inclusion of this BSC channel is the simplest word. We can just track a single scalar, look at its trajectory, and we will know whether this code ensemble will do good or not on this surrogate channel. Okay, so that's the motivation. And the basic idea, so after all those preparations that tutorials say, here come the meat, essential thing about our multiplexer design. So basically, we try to solve this constraint optimization problem. So the goal function, gamma is a decoding SR. So we desire it to be as small as possible, right? We want to increase the power efficiency, improve power efficiency. This in the quantity D is the multiplexer. So this function just emphasizes that this decoding threshold, the SMR, is actually a function of the demultiplexer design. That's the goal function. We're trying to minimize this SMR. And there are 5 different constraints. So this first constraint is here. It's upper bound on the error probability of all such channels. So we wish to make the maximum error probability of a particular channel to be less or equal to a particular error probability. So this is our error probability bound for all the sub-channels. And this one comes to the consistency of the variable node socket number. That's for the perspective of degree distribution formula. And this one, these 2 actually, this is from the variable node side, this is from the shape node side. So these 2 basically they cover the same set of constraints. And this 2 is the consistency perspective from the edge perspective. So this one is consistency of the total edge numbers in the pentagraph comes to this constraint. And last one is the consistency of the variable node allocation, because we know in our multiplexer design, each layer will receive the same number of coded bits. So this one essentially captures that notion. So after solve this constraint optimization problem, we know what this D will be look like, and we know what this D will be like. We know how to do the systematic rearrangement of those coded bits. Okay, that's story. And this is from diagram for the simulation, and we'll see this one. And this is the simulation results, and we have two H-maps here. So this red curve is the result using all the multiplexers. So this blue one is the one that we do not use any clinic of them. And the standing between is some DVB-C2 style bit interleaving. So we can see the gain we achieve here. This is for the case of 4K form using the short blocklets UABS2 code of rate 7 by 9. The second one, we still use the same code, but we decrease the modulation order to 1K clock. So this is our performance, this is the low interleaving case, and this is the DVB-C2 step. So we can still see the coding gain we achieve here. Okay, so the conclusion for the first part is that bit interleaving, right? It can help us do a great thing. It's multi-level modulation, because it can be employed to match the irregularity of code profile to the non-uniform parallel channel. This is in the context of cable channel. For the physical communication channel is WGN, but this notion actually can be extended to the wireless channel for the both the channels. Suppose we know the feeding gain, the fly feeding gain of each sub-channel. And also we know the profile of BP delivery can be configured via generic distribution, because generic distribution assumes the interleaving is conducted in a pseudo-random way. However, from the implementation perspective, we desire a structured interleaving, or in other words, we want some structure which can help us reduce implementation complexity. So therefore, we want to design a bit demultiplexer, and that profile of the bit demultiplexer can be configured under the useful framework of multi-edge type LDC codes. Okay, and finally, we know the distribution of the parallel non-uniform channel can be simplified by invoking a group or several BSC channels. So that's our contribution to this part of work. And the second part is the more reserved one. It's the hierarchical modulation. So how we do the hierarchical modulation? So you can see this is the diagram for this solution strategy. So this branch, the red one from here to here, is the legacy receiver, right? The lower branch from here to here is the superposition layer. So it's that now we add the layer correspond to supplement data on top of the legacy layer. Combine them together, use the house gain initial here, and then transmit them over the AWG channel, and then do the modulation and decode them independently. So by doing this, we reserve the structure of the legacy receivers, but we can hopefully add some more data rate on top of the first generation UABC system.
Are you really doing superposition with plus, or is this somehow a conceptual picture that you're actually doing QAM with the
I think this
higher order bits are the higher order bits in a constellation? Are the LSDs?
I will answer the question.
Huh?
I will answer that question with this picture.
Okay.
So, see here, see the pink dot here? These are the legacy layer. So they are 60 pop. That means okay. For example, this legacy layer, this legacy transmitter, receiver. So from here to here, and the modulator here will be 16.
So the answer is neither of my suggestions. What you're doing, you're actually doing qualm superposition.
Yeah.
You have qualm, and then you do a superposition of another QPSK symbol.
But it's not necessary to be two qualm. It can be one qualm plus a PSK, APSK.
Yeah. Okay. But so if you think of PSK, it's just a version of qualm. It is, right?
Yeah,
Qualm on a
yeah.
circle.
If it's QPSK, it is.
No, but even
Okay,
qualm
so
is
that's
just
the
generic
difference
thing
is
for
ATSK.
Always rectangular.
constellation.
You're right,
and-
you're right.
Right.
10% is ATSK, right? Amplitude and phase modulation, so it covers both.
Yeah. So okay. So I understand. Okay, good.
Okay. So this is picture, for example, about how we achieve this hierarchical population, 6 people qualm. So this 6 people qualm describe the whole constellation here. So it's not a standard square uniform spaced qualm. If you look carefully here. So how we do that is that, okay, now we superimpose QPSK on top of 16 qualm. So in a single space, we have a neat expression. So this X denotes the combined signal of the hierarchical population, and it can be decomposed into 2 parts, alpha plus beta. So alpha actually is a legacy constellation point, and the beta is QPSK, but this gamma is a complex scalar which used to adjust the orientation and the size of the superimposed constellation. So that's the signal space expression for this hierarchical population. And correspond to this picture, we know this legacy beta alpha is a complex constellation of 64 qualm, and this beta is a complex constellation of QPSK, but it's rotated by an angle maybe 30 degrees, something like that. And the power allocation between these 2 layers is gamma squared. So we assume this alpha and beta, their average power is the same. But then its power allocation ratio boils down to the square of this magnitude of gamma. Okay, so in order to do this, satisfy the make this legacy layer and the active layer to be heavy, we basically confront 2 conflicting requirements. So for the active layer, for this QPSK, right, we desire a larger growth. But for the legacy layer, we desire for a smaller growth. So why is that? That's because these 2 layers, they are decoded independently, so they will treat each other as theirs. So that's why we have this added layer will favors a large gamma. They want their own constellation to be as powerful as possible. Also it applies to the legacy layer. But because each other will treat the others as enemy, not as a friend, so they, from the perspectives, their perspective, they want the others to be smaller. So this, based on this constellation, we can derive the modulation constraint capacity. So that's different from the capacity achieving signal we know from the well-known capacity theory of channel. So we know the capacity achieving signaling for this transmission scheme over the Gaussian channel should also be Gaussian-like. But in practice, I think so far, no people will invoke this Gaussian signaling over the practical communication channel because a lot of problems such as the complexity and the peak-to-end ratio, something like that. So now we are more interested in studying the modulation constraint capacity, and we know because of the constraints on the constellation, it's not Gaussian-like. This capacity will be unbounded by the channel capacity. And how to derive this capacity? We use mutual information, this generic formula, and we do something like this. And in order to calculate this is how we do the numerical, how we get the numerical results for this capacity, right? And this is by adding just an S realization of random receive signal here. So this one will help us to calculate the modulation constraint capacity for a given constellation. And if we know how to do that, we will figure out which constellation will achieve the maximum capacity.
So what does that mean? A random transmit receive signal pair. Is that a vector code word, or is that
No, it's just a single
a
channel signal.
randomly chosen symbol?
Yes, from the constellation. So it's like now, suppose we have this constellation, right? But the interval type will be transmitting this one, that one. But how do you calculate the average brightness or the capacity of the entire constellation? That's how we do the simulation. Okay, so this picture just shows us some interesting results about the constellation mapping. And that boils down to this curve. So this one is the Shannon capacity. This is up. We cannot go beyond this because this is the optimal way to achieve capacity. And in reality, we have some population capacity. And we can do some uniform modulation constraint capacity. And this one is like, okay, in order to decode each bit independently, we do the block mapwise decoding. And we come up to this capacity. And we can also do the non-uniform constellation as I showed in the previous picture. We do the constellation mapping, which makes this one be more akin to the Gaussian signaling. And then we can achieve some capacity gains over this region. But in any case, no matter it's BSCM or modulation constraint, they will be unbounded by this Shannon capacity, but they will have different superiority over different SR regimes. And depends on the operation as far we can, if we only consider capacity, we can choose which one is, which will be our preference. Okay, so the capacity of hypercorrelation, we have some observations based on our previous pictures. We assume the independent decoding of two layers, the legacy layer and the IP layer. And these two layers, by doing this independent decoding, we do not need to do the multi-state decoding, do the degraded Gaussian channel. We simplify our life, which means we achieve a lower capacity, but this is not capacity for the degraded Gaussian broadcast channel, right? And for the capacity of a next layer, it's simply the mutual information between the constellations received symbol, the hierarchical modulation received symbol, and the transmitting next layer. And we'll treat the other layer as the noise. And in order to decode the other layer, we'll do the same thing. We'll treat the next layer symbol as the noise, and then calculate the information between this hierarchical modulation symbol and the
So I don't really understand. So I understand the capacity of the legacy layer, right? This additional constellation around each point is really a noise signal or an interference signal. But when you say you go back to the added layer, right? You're just talking about how do you think about the decoding or the signaling there?
The
Like,
decoding, yeah.
For that added layer, is the constellation just the? Could you go back a slide to a picture of the constellation? Go maybe this picture. Do you think of the information as just being carried by the blue signal points?
Mm-hmm. I think the information of the other layer is only carried by this two. So there's no joint encoding.
So what do you call the interference of the legacy layer?
I don't understand what you're
Well,
saying.
you're saying that the decoding on this blue signal level, right, is the you're saying the legacy layer is interference, and I don't see it. And what I see is
talking about the degrading notion, but here it's like, okay, the next layer you cannot change anything, so we'll treat the other guys as interference. That's okay. But for the other layer, they are told to do the same thing.
So-
They are only given at the transmitter, they tell them, now I'm transmitting ATSK, and decode, demodulate it, I think is good. They cannot.
Okay, so let's ask this question. For the advanced receiver, how does he do his detection?
There is no advanced receiver notion here.
Yeah, there is, because there's the legacy receiver who decodes the legacy thing, and then there's the
added, yeah,
the
added.
added the
It just added, but it's not that smart.
Okay, but if one is legacy, the other is advanced, right? Or added. Someone who's decoding the added information. How does he do his detection?
They do the detection. I think they maybe they will estimate this one first and sometimes.
Presumably, right?
And
I mean, you could do detection. You could do map on the blue signal points, right? Or you could do a kind of you detect what cluster you're in, and
I think he would want to detect the legacy point in the constellation and beat it with the other signal so that the product produces the small constellation.
So in that case, that's joint detection, right?
Yeah.
It's like you detect the legacy layer, you cancel it, and then you only get added layer. But you can do it separately as you suggest. But what you can do is you can firstly compute the error of the speed because it's already encoding thing in this case, and then you do the decoding.
maybe demodulator is a joint, as you said, but the decoder is independent. So the demodulating decoding is, let's say, this picture. So this one is like when they do the detection signal, right? So this one recognizes the legacy, the 16-talk, I think this one. And they also recognize the QPSK, I think this branch. And then they do the decoding independently.
So what does that mean? He recognizes the QPSK.
It just maybe do some match to the call center, some value, and make the ARR input and then propagate that to the.
Okay, so my point though is, okay, so do you have then a model of how that works where you rewrite the signals and interpret something as interference from the legacy system? I mean, kind of if that system works reasonably well, right? It means that the detection of what cloud you're in is really, really reliable because you're not only detecting the cloud, you're detecting the stuff, the structure of which one was in the cloud.
Yeah, I see your point.
So I think when you go to that kind of model, you don't really have any legacy interference.
Yes. So this one actually they recognize the hierarchical constellation.
Okay.
So the cancellation is done in the hierarchical modulator?
I mean,
Yeah, it looks like it, yeah.
Sure.
So you mean you don't have cancellation here?
I think so.
She
So
could.
now go to the
Could, but
go to the
don't
constellation.
have to.
The constellation diagram.
If you don't, I want to know what kind of detector you're using instead.
So, I mean, the impression I have from the hierarchical demodulator is that whatever the legacy point is, it zeroes in on that, and all you get is the 4-point constellation around it. And then
Yeah.
you demodulate that.
Once you right, and it's like you should have something pretty close to just
Yeah.
QPSK
The 4-point
on
constellation.
that little constellation.
Yeah.
Yeah.
Now I remember how I did this, this
Yeah.
part.
Well,
Yeah.
I mean, whatever interference there is related to the small probability that you're going to get the constellation wrong, the legacy point
Right.
wrong. If that happens,
I mean, you're out in space.
Yeah, right.
You're-
you did. But without that kind of an error, you have the same 4-point
So that
constellation.
error is more like kind of an outage or an
Yeah.
erasure or some bits
Yeah.
they're just wiped out and you're guessing.
Yeah. In fact, whatever that probability of error is, that's the probability of error or at least the minimum probability of error you're going to
Yeah.
get for the small constellation.
I think there's a notion of, who will you decode first? You have to decode both if you're a degraded. You have to look at the degraded model, right?
If you're the better guy, you're the better guy. You really end up decoding both. If you're the advanced receiver, who is
You have to decode both.
Okay, I will
Okay.
consider it later. Okay, so that's your generic picture, but now we have a practical picture, and then based on that, we can do some simplifications based on those practical constraints. So the first constraint is the somehow constraint of the cable channel. The cable channel is benign, but it's not hidden. That means, okay, we still have a budget for the SNR, for the power, and that's already bounded by 35 dB, but maybe in the next generation, they come to 40. I don't know exactly here, but in any case, the SNR is unbounded. It cannot be as large as possible. And that constraint is important because it actually specifies how large the constellation for the ith layer, right? If the power is something like that, in order to guarantee the service quality of the next layer, we cannot make the ith layer as large as possible because they'll be regarded as interference. And okay, so based on this first one, we have this observation. So it's unnecessary to consider very large size subconstellation for the ith layer due to the power constraint in terms of this P6 divided by N0. And the good enough options for the subconstellation will be QPSK, APKSK, and system form. So we choose this standard constellation because we know how to, we have some standard demodulator for this constellation, and it's easier to fabricate them together. And we also recognize that the notation of subconstellation doesn't make much difference because maybe they just play a very trivial part in the enhanced capacity, and they play a less important role than the magnitude, the power ratio between these two constellations. And because of that, if we are given the subconstellation, if we know it's a QPSK or APSK, so essentially the optimization problem boils down to the configuration of this magnitude. So this also simplifies our life a lot because previously, if we regard this gamma as a complex variable, we have to search for its or optimize its magnitude, optimize its angle. But now we know we can forget about the angle, we can focus on the magnitude. And that boils down to one-dimensional optimization problem. So this picture shows a basic idea how we design this graphical compilation while this constraint optimization for the capacity. So this objective function is constraint capacity, and we try to optimize the sub-constellation data given here in order to maximize the capacity of this ith layer, to maximize the data throughput for the superimposed layer. However, we need to consider this constraint. The first constraint is to guarantee the quality of service of the next layer. Next layer will receive some priority, and we cannot make the do serious penalty to their air performance. And we also want to I forgot what this means, sorry. And this one is about sum as a constraint, and this one just tell us, okay, this is the effective constellation after we do the power scaling here. Okay, so that's the constraint.
So Michelle, you're actually optimizing over the size of the constellation for the added receiver for the additional data. It's not just that you're fixing it as QPSK or some QAM for the
We can do it this way. We fix this QPSK.
No. When you conceptually write this optimization, you are thinking about changing the constellation size within
right.
the little cloud.
Yeah. If we write this way, that's true.
Okay.
But
all
in
right.
practice, we do stuff.
So beta is a constellation,
Complex.
a complex constellation, and gamma is just a scaling factor for that complex constellation.
Exactly.
Okay. And you take as parameters the input. There's an SNR, a channel SNR that you do this optimization for different versions of the channel average SNR.
Yeah, but the SNR has to be within some interval, so it's not like, okay, we go from 0 dB to 35 dB and we check the resolution as 0.1 dB. We do not do that. So let's look at this one. So we only consider this maybe rough range, but this even this rough range gives us enough evidence to make conclusions. So this division signal, because we do not have some.
But technically, right, I mean, you really have just a transmitter who has a power constraint. So to say, oh, we have a certain SNR of the legacy layer is kind of fake. What you really have is a transmitter with a certain power, and you could put a little more power into spreading the legacy constellation, and you know, and because the fact is, if you spread that, you know, and then have a sort of a tighter constraint, you could have then if you put more power into the legacy constellation and move those points apart, right? Then you have a smaller residual power budget for the added thing, and you get kind of a power constrained kind of modulation, right, for the added receiver. I'm going to call it the advanced receiver, right, for the additional data, right? On the other hand, you could reduce the legacy if you try for a certain amount of power you allocate to the advanced thing, right? Then you know, you can't make the legacy SNR too small, right? You have to keep it spread out. So I think honestly you ought to think about doing the two together, the optimization, because it's.
Yeah, this project is the first one in my internship, so it turned out this strategy is not adopted, so I didn't go further. This is a backward compatible solution, but it turned out
They didn't adopt this?
No, because during this
That's a
discussion,
practice.
they decided that they don't need this so-called backward compatible mode. They want to directly jump to the second generation.
Uh-huh.
So this is just a practice.
Okay, all right.
Okay, so this sounds.
You get a good idea, and it's squashed by a standardization committee.
Maybe for the third generation, I don't know.
Yeah, well, that's right. For the next generation, it'll be legacy compatible with this C2, and
But
you'll
you know, some
propose the C2 legacy compatible hierarchical.
Actually, we have proposed this hierarchy modulation in DVB-C, but it turns out no one use it.
Yeah.
So that's maybe
Why
game theory. So they don't want to have that one in C2.
Okay.
Okay, so this picture is result from previous data. We play with the 16 column and we put different power constraint on the channel SNR for the SAR SNR here. So 5 different SNR levels. So we see that for the next layer, right, if we fix the subpopulation of the ivy layer, if we increase this SNR, okay, the performance improves. So that for the next layer. And for the ivy layer, actually, it's the converse. It's because if we increase the, okay, this picture just shows how we play with different rate. So how much air performance can we get? So if we increase this code rate, which means we allow more data rate for the ivy layer, right? The rate, code rate plus the symbol rate will be added throughput. So this one will be the throughput capacity to the ivy layer will be larger. So that means, okay, we have to afford to allocate more power to this ivy layer in order to achieve a high throughput. So this is reasonable.
So what do you think the x-axis is? What's that eta naught?
Eta naught, I think, is the sun power.
So-
Rho is okay. We fix the ratio between these two layers. But if we want to transmit,
Yeah, okay, it's fine. I understand why the curve now looks
And
like
the-
that.
Michelle, can you move fairly quickly because we're
Yeah.
really
I'm
out of
done.
time?
Okay, now this is maybe the last one. So this is the capacity region. Suppose we take the X layer to 260 com and add a QPSK as add layer, and we play with different rates. And the intersection of these two curve, the up one is those ones that satisfy the X layer points, and this area under this line, straight line, is those satisfy requirement for the add layer, and the intersection of these two regions will be the mutually useful part for this calculation scheme. And okay, so that's the conclusion. And we know the happy manipulation is backward compatible because it won't destroy the structure of the legacy series. And we know the design of the modulation scheme for the added layer can be formulated as a constraint optimization problem. And however, the practical part constraint on the cable channels can make use of that to simplify our sub-constraint design. And finally, given the transmission power of haptic manipulation and topic bit error rates, we can achieve reliable power allocation regions and channel coding gains on those two-dimensional planes. Okay, so that ends my presentation. Questions?